In this video, I'm going to look at problem 50 from chapter 21. So let's do that. So in this problem, we have a thin glass rod that's bent into a semicircle of radius capital R, and a charge is non-uniform distributed along the rod with a linear charge density given by lambda equals lambda naught sine theta, where theta lambda naught is a positive constant. And so let's draw this. So I have a semicircle, glass rod, and we're looking at the point P at the center, and there's some non-uniform charge density distributed over this. This is lambda naught sine theta, and that theta is this angle as measured from the horizontal. And in fact, they actually give you a coordinate system. So I'm going to draw the coordinate system with the origin at P. So this is Y, this is X. So that's the angle it makes with the positive x-axis in the counterclockwise direction. And we are to calculate the electric field at point P. What's this? Right, so both the direction and the magnitude, they're asking this as a vector. So what does this look like? Right, so this is sine theta. So over here, sine theta is going to be 90 degrees. So it's going to be, sine theta is going to be 1. And then over here, theta is going to be minus 90 degrees. Okay? And so sine theta is going to be minus 1. So we're going to have, this is going to be large in magnitude and positive over this point, a lot of positive charge here, and then it gets, less and less. Over the x-axis it flips, then you start picking up negative charges, and then as we come here, there's a lot of negative charge over there. All right, so it changes smoothly as you go from this top point to the bottom point, and it flips sign. For this point it's 0, but it flips sign over the x-axis. And they're asking for the electric field. Now, ironically, for these problems, the circular rod is somewhat easier than a linear rod, which we have looked at in a number of examples and problems, because all the points are equidistant to the center. Now, if you're looking at any other point than the center, this will of course be a much more complicated problem. But here we're looking at the point at the center, so this is easier because they're all equidistant. So we don't need to calculate the variance with respect to the distance. Right? Whereas for a rod, you generally need to do that. But here, the electric field that's produced by all of these points is going to be different, simply because the charge from each point is going to be different, right? So if I take a little part over here, let's say of length, let's say call this dh, and that dh is going to correspond to some dq, and that dq is just going to be lambda times dh, but in this case, it is going to change with the angle. Right? So this makes it a little bit more complicated. Now the first thing you need to look at in problems like this is to see if there is any kind of symmetry. Right? And in this problem there is a symmetry. It's a little bit of a subtle one. So if you flip up with down and positive charge with negative charge, you get the same picture. Right? So that's the symmetry in the problem. So if you just flip this around and then say all the negatives are positive, all the positives are negative, you get exactly the same configuration. The electric field here will not change at all. So can we exploit this? It turns out, yes, we can. So let's look at this point over here, that this is going to produce some, this is the positively charged part of the rod, this is going to produce some electric field over here, like so. Okay? And then let's take the corresponding point over here, that's going to produce an electric field like so. Okay? So the horizontal components of those two electric fields produced by these two charges are going to be equal and opposite to each other, they'll cancel. And the vertical components are just going to make each other larger. So we are going to end up with a purely vertical electric field. Let's make these a little bit smaller, so my vector sum looks more reasonable. But this is not, there's nothing special about these two pairs. We can take, for any point on the upper part of this half ring, we can take a corresponding point on the lower part, which means we can always pick up some pairs, and the vector sum of the electric field of those 2 points is always going to be vertical, which means that our final electric field has to be vertical as well. Right? This means that we only need to calculate the y component of the electric field. So let's write this down. So the electric field strength is going to be just the y component, and this now we can actually write as a sum of or integral of infinitesimal electric fields. Right? So that is going to be a component of the electric field produced at an arbitrary point. Let's say that arbitrary point is at some theta. So if that is theta, let's extend this. So this is my electric field, this is theta, this is also theta. Okay? These two angles are going to be the same. I'm looking for the vertical component, this component of that electric field, and that is going to be given by the sine of angle theta. Okay? So this is going to be some sine theta dE. Okay, now what is that dE? It is the electric field produced by this infinitesimal charge over here, and I can write that to be sine theta dq, the amount of the charge, divided by 4 pi epsilon naught capital R squared. Okay? All the points are equidistant. It's always a capital R, so I can just simply write this down. Now that dq is going to be given by this. It's also going to be proportional to sine theta. So this is going to be sine square theta lambda naught dH divided by 4 pi epsilon naught R squared. Okay. Now, here we have the problem of writing this dH in terms of theta or theta in terms of dH. Okay, we need to do this. Now, if you look at the previous problems where you were looking at rods, these dH was lying along the y-axis or the x-axis. Then you could identify it as either dy or dx, right? And then you might think that, okay, here it's just going to have two components. And it's going to have a horizontal component given by something times dx, and it's going to have a vertical component given by something times dy. Right? And these are going to be proportional to cosine theta and sine theta, something like that. Right? And you could do it that way. You could, of course, do it that way, and then you would also need to write your sine square theta in terms of x and y, which you can do. That's certainly possible, but that's really making things too hard for yourselves. So instead of insisting on using Cartesian coordinates, we can actually switch to polar coordinates. That's also a perfectly viable way to describe what's going on, and in this case, it's actually much more practical. So instead of using x and y, we can use r and theta. And if you use r and theta, then this dH is really corresponds to moving in the theta direction. Okay? You're not moving as you're moving along the circle, whose center lies at the origin of our coordinate system. You're not changing your distance to the origin. You're just moving along the theta direction. So I can express that dH in terms of something times d theta. Okay? So this dH is something times d theta. And what is that? Well, let's draw the d theta. So let me use a different color of chalk here. Okay. I don't know if this actually comes out clearly. So this is going to correspond to moving this much. Okay. So we are going to cover this length dH if we move this much d theta on the angle. Okay. So we are just, as we are moving over this, let's say, over this half ring, we are just changing theta. Now, to cover this part of length dH, I need to go in theta direction, a distance of d theta. Okay? And this dH is going to be given by something times d theta. It is just r times d theta. Okay? Why? Well, that's the definition of radian angles. Right? So if you're measuring this d theta in radians, then the arc length that it covers is going to be just the radius of the circle times the angle. Okay, and here this arc length is just dH, and this angle is just d theta, and our radius is just capital R. So this is just definition of the angle theta, d theta in radians. Right? So this also tells you that when you're trying to, we are going to write this in terms of theta, but because we have actually written this by using the definition corresponding to angles measured in radians, we have to write these angles, these limits, also in radians. Okay? Now, what does this correspond to? Well, we can say that theta is going from minus pi over 2, this negative right angle to pi over 2, or you can say that it goes from 0 to pi over 2 and just multiply it by 2. Because remember, there is going to be a contribution to the horizontal component of the electric field from the lower part and the upper part, and they are equal to each other. Because they are equal to each other, I don't need to calculate them separately. I can just take this part and multiply by 2, which is what I'm going to do. So I'm going to say this is 2 from 0 to pi over 2. I can take some of these out. So I'm going to take lambda 0 out. I'm going to take 4 pi epsilon naught r square out. I'm going to end up with 0 to pi over 2 sine square theta. There is an r here, so I'll take that r out as well, r d theta. Okay, now I need to take this integral. Now, you can look this up. You can find this in the appendix B of your book, but you can also take this. It's not that hard if you know the half-angle formulas from your trigonometry. So cosine 2 theta is going to be cosine square theta minus sine square theta, but I can write this cosine square theta as 1 minus sine square theta. So this actually becomes 1 minus 2 sine square theta, which means that sine square theta is 1 minus cosine 2 theta divided by 2. Okay? So let's do that. First, let's simplify what's going on here. 2 cancels this, cancels, so this is lambda over 2 pi epsilon naught r from 0 to pi over 2. I'm also going to take 1 over 2 out, so this becomes 4, 1 minus cosine 2 theta d theta. Okay? And to take this explicitly, I'm going to call 2 theta u. So then d theta becomes du over 2. And this is going to correspond to u equals 0. This will correspond to u. Write this down. We're going to have lambda over 4 pi epsilon naught r from 0 to pi 1 minus cosine theta, cosine u, sorry, du. Okay. So this d theta is du by 2. I took that 2 over. I can take that 2 over here. No, I can't. Sorry. Can I? Yes, I can. So it becomes so. Okay, so the first part of this integral is trivial. It's just pi. Okay, it's 1 integrated from 0 to pi du. It's just pi. The second part of the integral must vanish because cosine function looks like this. Okay, so this is 0. This is pi over 2. This is pi. So if I integrate this from 0 to pi, this area cancels with this area. That integral must vanish. So it just introduces a factor of pi, and this is going to be lambda over 8 pi epsilon, the pi goes away, lambda 8 pi epsilon r. Okay, this is surprisingly simple. Well, I made one mistake, which I need to go back and correct. This one here, this needs to have a negative sign, okay? Because well, actually here, already over here, it needs to have a negative sign. This is positive, so it needs to have a negative sign here because the way I draw my coordinate system, the y component is negative here, okay? Which means that this dy is not the magnitude times sine theta, it's the minus magnitude times sine theta. So I need to introduce a negative sign all over the place. Here, here, and finally here. And if I need to write my electric field at point P, I'm going to say point P is minus lambda 8 epsilon 0 r j hat. Okay? So a lot of people go through this and then forget that you actually need to write the electric field at that point. So just don't forget. doing this. Right. So for the part B, they're asking us to determine the acceleration, magnitude and direction of an electron placed at point P, assuming r equals 1 centimeter, and lambda naught is 1 microcoulombs per meter. So you just calculate, the force is going to be just charge of the electron times electric field. This is negative, so it's going to be an upward force over there. And then to calculate the acceleration, you need to divide your force by mass of the electron. Now, mass of the electron is tiny, and they are giving you some lambda naught to be like 1 microcoulomb, which is still very large with respect to the charge of the electron. So I expect that this acceleration is going to be something huge. I'm not going to calculate it. You just need to substitute these numbers and make sure that you get something in the positive y direction. The acceleration of the electron is going to be opposite to the electric field. So that's the only tricky part. And I do expect this to be some very large number, because this is a macroscopic distance. It's 1 centimeter, but this doesn't really matter. It's going to produce a considerable electric field over here because it's microcoulomb. A microcoulomb is much larger than the charge of an electron. So I expect this electron is going to feel a very big acceleration due to smallness of its mass. The force is not going to be big, but the acceleration is going to be very large.